we look into material properties and stress strain diagram, which was introduced by Thomas Young and which gives us one of the most vital material properties known as Young's modulus. Young's modulus is a theory that defines if a material is within the plastic limit or outside the elastic limit. So Thomas Young did these experiments in 1810 and developed the theory of elastic deformation of materials. He was the person who discovered Young's modulus, the tensile test currently performed on any system that has become a very important experimental test. It helps in determining the Young's modulus along with other material properties and possible failure. The picture which you can see on the right side is an ideal example of a testing rig that is used in performing the tensile test. It is mounted on a universal testing machine, as you can see, and then the specimen is pulled. These are some of the examples of dog bone structures for rods. However, different analysts have different ways of doing this type of a test. Usually, the dog bone test is carried out only when there is availability, and in most cases the labs that perform these tests do them using the rectangular shaped simple specimens. Other than that, we can also find cylinder shaped specimens for which the grips are different when compared to the ones for rectangular ones. For samples and accessories, material samples are tested in a variety of geometries. However, with availability, the most common one is the dog bone structure. Several techniques are used for measuring the dimensional changes in the structure being tested accurately. The devices that are shown here, in which one being the strain gauge, which is usually mounted on the specimen, and the other one is a non-contact extensometer, which usually uses quality of video imaging capability to capture the movement of the material when it is pulled apart. Now let us see some equations that are used to calculate stress and strain. We have already come across these equations, but to make it clear, we will go through them again. In this, we can already see that the gauge length is given. Considering the load extension behavior of materials, Young converted them into stress strain data. Engineering stress and strain are calculated based on the sample cross section as sigma is equal to internal normal force divided by the original cross sectional area, and that can be denoted as P divided by A naught. Same way, epsilon, which is the strain, is equal to change in length divided by the original length, which is denoted as U divided by L naught. These are equations from whatever we saw earlier. And we also saw that we usually do not consider true strain and stress for normal problems due to their inconsistency. But instead, we use these equations to keep the true strain and stress in our calculations intact. So, how does an ideal stress strain diagram look like? Here, in the given figure, the true and engineering stress and strain are shown for a steel specimen that is loaded to its failure. So, as you can see in this graph, there are two curves that run throughout. In the linear region, the graph doesn't change a bit, but only after a certain point that the graph starts to move up by a certain distance. So this movement, which is going up, as you can see in the figure, is known as the true stress strain data. So this is how the material is supposed to behave without any other aspects. However, when it comes to engineering, we as engineers like to keep things safe, and therefore to keep things safe, we make a new graph which is known as the engineering stress strain graph. And this engineering stress strain graph has your ultimate stress as the highest stress, and fracture stress is usually lower than the ultimate stress. However, in the actual stress strain graph, which is the true graph, as you can see in the figure, the fracture is actually higher, or we can say way higher than the ultimate stress, but the engineering stress strain graph is usually good enough for us. Next, we can see that the graph is divided into two major regions, which is the elastic region and the second one is the plastic region. In the elastic region, material has an elastic behavior, whereas in the plastic region, the material has a plastic behavior. Again, this plastic region is divided into four parts. we also should have this in mind that the plastic region is specifically for ductile materials. I mean, the 4 parts that is divided is for ductile materials and not for brittle materials. Also, we don't have this big a stress strain diagram in the tensile region. In the initial stages, we have the yielding process, then we experience strain hardening. Finally, we finish this with the necking, and that is the region where the material keeps breaking. The highlighted region which you see in the diagram, which is red in color, is where all the elastic limit samples are present and all the elastic limit calculations are done. So now this region gives us the entire linear relationship between the samples, which is used in the majority of the calculations. We have a few points here which will be introduced later as we go on further. So on the left side of the graph, the first point, which is sigma prime F, is basically the fracture stress. The next point, which is sigma U, is the ultimate tensile strength and is the highest stress when it comes to engineering data. However, for the true scale, it is completely different. Then we have sigma F, which is for fracture, but this sigma is not that critical to find. But we need to understand that sigma Y is when the material is trying to yield. And then we have sigma PL, which is when the material is in the plastic region. Now we can see that elastic region has the elastic behavior and the plastic region has the plastic behavior. And due to this, yielding, strain hardening and all those steps finally come to a place where the material failing happens. One important thing to understand is that inside the plastic region, the deformation that is happening to the system is permanent and cannot be changed. Whereas when it happens in the elastic region, the deformation is recoverable and it can be changed, which can also be called as it can be cured. Some important points to be noted here is that Young observed that the sigma epsilon slope was constant for any material independent of the sample geometry. This should be same for any homogeneous material system. Also, there is very little difference between engineering stress and true stress. We can tell this from the diagram, as we can see that the difference in the graph only starts from the strain hardening region and deviates a little bit from there. Hence, there is very little difference, and this difference comes into play only when designing purpose is involved. We have to make sure that the material is safe enough, the design is safe enough, and understand the different materials we have in different ways. So with that information, Young found this derivation on his name, which is Young's derivation. His derivation made sure that the stress strain slope for a particular material was observed to be constant and was independent of the sample geometry. This is true and should be same for all homogeneous material. A good indication of understanding the fabrication of composite material is having a near constant sigma epsilon slope when tested at different locations. These observations led to the definition of modulus of elasticity, or Young's modulus, which is represented by capital E. And it has a similar graph to what we saw for stiffness. However, the X and Y axis are changed here. It is plotted against stress and strain and not against load and elongation. For uniaxial loading, we will note that sigma is equal to E times epsilon, or E is equal to sigma divided by epsilon. Below here, we can see some metric properties that are standard for various materials. Mild steel has a Young's modulus of 210 gigapascal, while aluminium has only 70 gigapascal as its Young's modulus. As we go on, the most lowest Young's modulus value is for rubber, which is 0.04 gigapascal. So therefore, we can say that mild steel has better performance in the elastic region, whereas rubber is not that high, which makes it a very bad material to be used during building constructions and other aspects.